Okay, so let's look at the equivalence circuit. Okay, okay, so let's look at the equivalence circuit. So to draw a circuit, just like let's draw the transformers. So if you remember clearly, for transformers, we have what the transformer leakage inductance, right? We have the primary resistance. We have what magnetizing branch. Okay. So then we have this. Okay. So we have the supply. So this shows they are not electrical. The primary and secondary are not electrically connected. So we have the secondary within over here. They have the secondary leakage inductance. Then we have the resistance. Of, okay. Yeah. So then the load is connected over here. Is that okay? So it's the same thing for the motor. We have to have what the stator leakage inductance. So we call it less. Then we have the resistance RS. Then we have the magnetizing branch. So this magnetizing branch very important. Okay. So we are going to call it either LM or LO, whatever it is. Then we have the field winding. Then this was magnetically coupled the rotor winding. Then the rotor lead reactance. We call it LR. We have what resistance. Is that then these are short circuited together. Is that okay? So this is going to be how from the transformer we are going to get what that's of what the motor. Okay. Yeah, so that's what, so this is like an ideal transformer. Okay. So as initially that the ray is prevented from moving, that means the rotor is at was cancelled. We set we have two sets of three phase winding. That's you have one set on the stator and you have another set on rotor. So we have two sets of what phase winding sharing a common magnetic path. Is that okay? The three phase transformer. This is like three phase transformer. The three phase transformer to you have what three phase you have what three phase on the primary side, then three phase on what the secondary side, and they share the magnetic medium. Remember, transformer is what a stationary or device. Okay, it doesn't it has no moving part. So right now we are looking at the motor at a standstill, right? That which means nothing moving in the motor yet. Okay. So then this looks exactly like what a transformer. Okay. So that's why I drew if check here. So you see that okay, this is just RR. Is that okay? So then this will be VS with a speed of what omega what E. And this place is going to be what? Should I say VR or R? Okay. And frequency is what omega sleep. But if it happens that, or as we are looking at that, what that it is stationary, as we're looking at it in stationary state, then omega sleep will be equal to what omega E. So then, if that's the case, then this is also going to be what this is also going to be what omega E. Is that okay? So if the rotor is allowed to move, the effect might be considered. So now we've looked at it at standstill. The moment the rotor begins to move, two things are going to happen. First one is the induced EMF in the rotor is what um, used. That means it's going to depend on the relative velocity between rotor and field, which I've already explained. Now you are going to get a certain voltage. That voltage we said what is a fraction of what the EMF used at was start, and that fraction was the slip. Then now omega slip is no longer equal to what omega E. The moment the rotor begin move, the omega slip is now what equal to what omega E minus what omega. Okay. So now the frequency of the voltage induced in the rotor depends on what the relative velocity of the rotor with respect to what the rotor. Okay. So that is why as starting we had this to be this. Okay. So then starting your impedance is equal to what? At starting your impedance is equal to R plus J omega E L R. Okay. But as the motor begins to move, your impedance now changes to what? R plus what? J S omega E R. Is that okay? And when you were stationary, your V over here, V2. Okay. So if this V1, okay, this is V, this will be V. Okay. So your V2, as time your V2 is equal to what? 1. Right? Now, if the motor is moving, then V2 is now equal to what? S what? V is out. So that means your current starting, I've already written, as starting, remember as in your, as starting V2 is equal to what? 1. Right? So starting you are going to have 1 divided by R plus what? J omega L R. But as the motor begins to move, your current now is equal to SV1 divided by R plus what? J J omega sleep. So as it begins to move, your the frequency is no more longer omega is omega hot sleep. So omega sleep dot S omega hot E then R. Then if you divide through by S, then get your IR equal to what? Your IR equal to V1 divided by what? RR on S plus what? J omega E L R. Okay, if that's happened, then your circuit becomes this way. So you still have your static inductance, you have resistance, you have the magnetizing branch over here, then you have the okay, so this LM. Then now this becomes you have what LR over here. Then this becomes the resistance has become R on what S, right? Okay. So the question is that now V2 here is going to be what? V2 omega A, right? Question is why do we have to convert to this? We are the answer is we are going to but initially it was just R. Why did we convert to R on S? Okay. So why did we convert to R and S? It's because when the motor is moving, the slip is no longer omega A. And we want to refer this to the primary side. Okay. We want to refer this to the primary side and we want to have the frequency set the same because Vs over here has omega E and the V1 over here has omega E. So we want all of them to have the same frequency. So for all of them to have the same frequency, then your this has to be divided by what is, for all of them to have the frequency. Then if this is not the case, then we can refer this set over here to what the star side. Then if we refer the theta side, then we have to have something like, so we have the cage reactance, then we have the which is the resistance of the theta, then we have the magnetizing what branch, then we have what, so now we've replaced to what the theta side. Oh, sorry, this should be everything. So this should be a resistance. Is that okay? R on what? Okay. Okay, now this is our equivalent circuit. This LS. Okay, so now let's get into dialysis stage. Okay. Yes, already talked about this. Okay. So now we now have our equivalent circuit. Let's see what happens. Okay, I've already done this. Okay. So again, the magnitudes only. So I1 is equal to I2. The I1 is here. Okay. So I1 by here. Um, this current here, I2 here, the magnitude of I2 is equal to magnitude of I1. Not I1 like, if you take I have I1's magnitude what? Eh, an angle what? Theta 1. Is that okay? I2 has a magnitude I2 and angle what? That 2. Saying that what the magnitudes are the same doesn't mean their phase is also the same. Okay. So I1 is what? I2. Okay, remember this. So we are saying that the phasor magnitude since I2 and 1 are for different frequencies. Is that so? Because they are different frequencies, that we had to what? Rewrite them at what? At the same frequency omega e. Okay, so that was what R on what S. Is that the V2 is also equal to what? V1. The V2 you see over here. Okay, the V2 you see over here is also equal to V1. And in this case, in this section, the only the magnitude are what equal, the bases are what different. Okay. So then if we want them to actually be the same, then if the magnitudes are the same, then we will have to rewrite this one in terms of since magnitudes are the same, the frequencies are they want to rewrite this in what we have the same frequency as this one. That's why it's also part of why this become what R on what. I hope this makes sense. Yeah. Yeah. So again, only the magnitude as one at frequency of omega v2 is at what omega slave. I've already explained that. So it also be shown that the phase shift between I1 and V1. So this is one and this V1. We are saying that the angle between I1 and V1, let's theta um, theta s, okay, it's equal to what the angle between I2 and 2. Let's call it theta r. Is that and this angle is the power factor angle. Okay, and how do we define power factor angle? Factor angle is equal to the inverse of what the reactance divided by the resistance. Is that and what the reactance in this is? The reactance here, okay, is going so that's going so theta r here. Since theta is equal to theta r is equal to what? Tan inverse of what? Omega slave LR is that going to be the x, the reactance divided by what r. Let me write well. Theta r is equal to the tan inverse of the reactance which is omega slave times LR divided by the resistance RR. Is that okay? Sure. So that's what you have right here. So he already explained this, how we manage share this. I've already explained this. So now that we them to have the same frequency, then we can say what V1 yes is equal to what their frequencies are now the same. Now let's look at an example concept. So this circuit, you are going to give a certain electrical power. Okay. This a motor takes what? An electric power and gives you a mechanical power. So if you give this an electric power, this power is supplied to the stator. So then this is going to cause current. So if it applies voltage Vs, this is going to cause what? Is flow. Okay. As Is flows through this a resistance. Okay. So then there will be a drop in what? There will be a drop here of or some power is going to be lost here. That power is what? P is equal to the current is flowing through resistor, which is is squared times what? Rs, which is what? Resistance. And after part of that is lost, you are now left with what? Some amount of power, which now goes into the egg, into the rotor. Okay, so then you are going to have air gap power, which is the power left after some have been consumed in the what? The stator, which is the air power. This air power is equal to P in, that's the input power minus what? The RS. Is that okay? This power is what goes to the rotor. As it goes to the rotor also has resistance. So you have a certain current IR flowing. RR, there will be current through the rotor. So this power is moves towards a magnetic medium to the rotor. Then there will be some losses in the rotor as well because the rotor has resistance. And the loss is what we call what P slip. So the total power that gets a rotor is what? The mega power PAG. Then some of this power is going to be lost in the rotor. And that power lost in the rotor is called the P slip, the slip power. Okay. This uh, after this loss in the rotor, then the power that will be left, what is going to what produce the mechanical power you are looking for. Then the Pmech should be equal to the total power that goes to the rotor, which is what the PAG, minus what the one is lost in what? That is lost in rotor, which is what? P slip. Okay. So and the resistance we have over here, the resistance RSS can be divided into two components. Okay, that means that is part of this resistance is what is producing the mechanical part, and part of this resistance is what is producing what. So part of this power, uh, RR on S, part of it produces what. So let me draw it. So this is RR on S. So this power, the total power that gets here is into the mechanical power and the that is lost. So that means a component of this resistance producing what the mechanical power, and the component of this resistance is producing what the loss. Is that okay? Hello,
Hi.
welcome.
Thank you.
Okay, yes. So as I was saying, so part of this power R on is what is producing the mechanical power, and part of this is producing what the losses. Okay, so then this like putting resistors for series. Is that okay? Because at the end of the day, the thing is going to flow to the root. Is that okay? And say that okay, this is part that is produced what the losses. That part is what the resist. the resistance, and the part that's producing the power is what? The that one is a minus S on what S. Okay, so this is what producing the mechanical power. Okay. Then this is the part that's producing what the which is the P slip. So that if I put this together, at the end of it should give me this one to have what R plus what. If I expand this, going to get what R S minus what R, because this would be RRS on S. This will give me this. This and this will cancel out. At the end of the day, I'll still get what RR on what S. This is the part that's producing the makeup power, and this is the part that's producing the loss. So if current flowing through, or if the current flowing through this is IR, then if I'm determining the P sleep, this sleep should be equal to what? The square of current flowing through, which is IR, so times what the resistance, which is what is. So this one way to calculate the slip power or power that is lost in the flow. If I want to determine the mechanical power, I can then I'll say the mechanical power is equal to what? The square of the current flowing through this resistance. Since this is what is producing the mechanical power, that gave me what IR was square. Then times what the resistance, which is what R minus what 1 minus S, all what S. Is that okay? So this find the mechanical power, this I find the slip. Is that okay? So this one way you can. So I will not ask you to like wait till we find the we do the top formula and just choose the formula. Is that okay? If you know how this release come back, it is to work with it. Okay. I hope we are doing. Okay. Let's go back here. Yeah, so I've already explained this. So there's an input part. Part of it is lost data. The switch the EGA power goes to the row. Part of it is lost the PC, then the rest produces for mechanical power. This is what you're actually interested in. But now let's see if first the sleep is going to have what the power that is and the power the use power. Okay, so we have P the input power. We know in power, if you want to find the input power, the P in is what? The supply voltage times what? The supply current cause what? The angle between. Okay, we call this um, theta S. Okay, so remember I said that everything we are doing here is per phase. So this is our input phase. So if I get the total power input, this is going to be what 3 IS what theta S. But we are using what uh, the phase balance. Okay. Then when this power goes, part of it is lost the theta, which is what PS, which is what theta square times what theta resistance. Then part of this power goes in what with the PAD. That's what goes to the rotor. Is that okay? And we've already established the fact that the PAD is equal to the power input times minus the that is lost in the state. Then the power that goes into the air gap. Let's come back here. The power, so this is the power that goes to the air gap. The power that goes into the air gap, PAG, is equal to what V1 per phase. So this is V times what I1 cause the angle in them. So that will be what theta. Uh, so this was yes, this will be theta R because we said this current is equal to what this current, and we said that theta S is equal to what theta R. Is that yeah, the phase we have it. The phase being this and the phase between this point and the voltage is because equal to the phase between this current and the voltage. You said that was, and this we even said this is how we calculate that phase. Is that okay? So the PAG is equal to V1 I1 cos what? Theta. This per phase. You want to get a so on, you multiply this by 3. Is that okay? Okay. So then we have P in to be equal to VS IS also, and we have PAG to be to V1 I1 cos PR. Then the slip part is also giving us PAG equal to what? V2 I2 cos what? This. But we know that V2 is equal to what? SV1. So then we can say that the PAG equal to what? Uh, yeah, the PAG should be equal to SV1, right? I think I'm getting something. Okay. Okay, yeah, PhD equals to, so this is a P split. Sorry. So then, okay, so this P. So then, if that is P split equals to, in place of U, we substitute was SV1, right? Then, um, we substitute L1. We know that the I1, I said this L1 is equal to I2. So then, this will have I1, then I have what? Cos pi R. Okay. And we know that's what the mechanical power is equal to the delta power which goes to the root minus what the P is away. Then the mechanical power should be equal to what? This PAG, which is 1 I1 cos of theta what R minus the P which is what S1 I1 cos theta R. So then if we factorize, going to get to V1 I1 cos what theta R times what 1 minus S. But whatever we have here, that is what PAG or the X power. So in the mechanical power, if you know the total power going into the rotor, want to find the mechanical power is equal to what? 1 minus S times what? The X power. Okay. Then from here to we say what? The slip power. The slip power equal to what? Remember, whatever we have is what? The Edgar power. So it's equal to S is what? The Edgar power. So now we know. So now we know that slip is equal to what? S is what? The Edgar power. We know the mechanical power is equal to what? 1 minus S times what? The Edgar power. Okay. So if you know the Edgar power, this one we can find the mechanical power. Is that okay? Okay. So let's go. We've already determined that mechanical power can be found by the square of the current passing through that resistance that we showed earlier. Square times what that resistance, and that resistance was RR is what 1 minus what divided by S. There's another way we can determine this relation over here. Okay, and that way is we say what P slip is equal to SPAG and P mechanic is equal to 1 minus PAG. So from this relation, we can make PAG the subject. PAG what? P slip divided by what? So then we can say the mechanical power is equal to what? 1 minus s divided by s times p slip. But we said p slip is equal to what? R squared times what? RR. Okay. So then P mechanical should be equal to what? 1 minus S all divided by S times what? IR squared times what? RR. Oh, yes. Then we've gotten the same relation. Okay. Yes. So now let's do our talk. Talk. Because at the end of the day, yeah, the mechanical power we want. So how do we determine that? Okay. We know that torque is equal to, or we know that power is equal to times for speed. Okay. So power is equal to what? Times for speed. Is that okay? So if I want torque is equal to the mechanical power divided by what? The mechanical was. Is that okay? I know how to determine mechanical power. I know mechanical power phase or the total mechanical power should be equal to the 3 times the power per phase, which is what? 1 minus S on S times what? IR squared times what? R. Is that okay? So then I need to determine how, and this what is left. If I get this and I divide this by whatever I have here, I should get what my total torque. Okay. But we know that mechanical speed is equal to what? Electrical speed. I explained this at the beginning of this tutorial. Mechanical speed is equal to electrical speed divided by what? Whole pair. Okay. But we know that omega s is equal to what? Omega e minus what? Omega r, all divided by what? Omega e. Therefore, s omega e should be equal to what? Omega e minus what? Omega r. Okay. If I group like this, I'm going to have s omega e minus, or I'm going to get omega e minus s omega e to be equal to omega r. So then omega e times 1 minus s should be equal to what? Omega r. Is that okay? Where this is the rotation, this is the synchronous speed. Okay. So now, then, so what will be omega e? Omega e, or what will be, so this omega r, right? So then I can say, uh, what do I want to, so then what will be omega e? So omega e will be equal to omega. I'm not sure I written the right thing. Okay, so omega e should be equal to what? Omega r, which is the rotor speed, divided by what? 1 minus what? S. I can say what my omega m should be equal to omega r divided by what? P, which is rotor speed in radians per second, with the electrical rotor speed in radians per second divided by so exactly. So that is what you have. Or no, I think it is. That's right. So this shouldn't be the synchronous speed. We are dealing with the rotor speed, right? But if you are looking for the torque that is produced, okay, you use the speed and shaft, right? So it is the power that is produced. If you are looking for the torque, the power that is produced in rotor divided by what? The rotor speed. Okay. Now, the rotor speed, the mechanical rotor speed should be equal to electrical rotor speed divided by what? 4 pair. And we know S omega E is equal to what? omega e minus what omega r. So equal to what? 1 minus s omega e. Is that okay? Because the reason why we want to write this in of the synchronous speed is that once I know the sub frequency and I know the number of poles, I can determine what the synchronous speed. Is that okay? Once I know these parameters, I can determine what synchronous speed. Sure. So if I come and set this into the going to get what omega m should be equal to what? Minus s times what omega e divided by what 4 pair. Then that will be what my omega m. So now I can find my torque. I said what is T is equal to 3 times what power, and the power is what 1 minus s divided by s times IR squared times what this. Okay. All this times 1 over what omega n. 1 over, look at omega n. We said omega m in this is going to be what? 1 minus s. Is it 1 minus s? Okay. It's going to 1 minus s times what? Omega e divided by 4. So 1 divided by this is to give us what? 1 minus this is to give us what? 4 divided by what? 1 minus s times omega e. So then this cancel this. So our total torque will be what? 3 times IR squared times R times the full pair, all divided by what? S omega E. Okay, so we made progress. Okay, so if you know the current through the tube, you know the rotary distance, you know the full pair, the synchronous speed, you determine the torque. What if we don't know the current? Okay, but we know a voltage. Okay, so this current IR, as we saw earlier, is equal to what? 1 divided by what? RR on S, so J omega E LR. Okay, then the magnitude of IR should be equal to what? Um, you know how to find magnitude, right? Find the magnitude of this divided by the magnitude of this. And the magnitude of this voltage is to what V1. If you are find the magnitude of this, is going to be what? Root of R on S. Also RR squared S squared plus what? Um, okay, so it's going to omega E squared LR squared. Exactly, that will be so that will be the magnitude of IR. Then here IR is so if you square this, that's going to give you what? V squared. Then that square is what cancel this. Okay. Then at the end of the day, I will have IR squared should be equal to V1 squared divided by what? R squared on what? S squared plus omega E squared LRO squared. I hope that means. Then if we can insert whatever we did into the, we are going to get our torque to be equal to 3 times v squared. Remember, everything we are doing here, the parameters here are what? Per phase parameters.
RR times what? P. All divided by what? S omega E times RR squared on what? S squared plus omega E squared LR what? Squared. Okay. Okay. So then this should be equal, if I expand this will give me 3v1 squared RR times P, all divided by what? If I expand this, I'm going to get omega E R R squared divided by what? S, right? Plus omega E to the power 3 S times what? LR whole squared, right? Then this can be further written as, if I divide through, if I multiply everything by S, I'm going to get what? 3v1 squared, right? So if I multiply here by S, denominator by S, 3v1 squared RR times P times what? S, all divided by, then I'll get what? Omega E RR squared plus what? S squared omega E cube L what? R squared. Is that okay? So then this becomes the relation. So you can you can integrate, you can differentiate this with respect to what? The slope. Okay, then find the point at which you are going to, the slope at which you are going to have what? The maximum torque. So that will be what? dt e d what? S. You can use the quotient rule to do that. I'm not going to do that. Okay, yes. So that will give you the total torque which you have over here. Yeah. So when the induction motor is connected to a fixed frequency, fixed amplitude voltage, then these parameters here are going to be what? Fixed. Is that okay? These parameters here are going to be fixed. So what this means is we have TE equal to 3VI squared times RR times what? Times P what is times S, all divided by what? Omega E RR squared plus S squared omega E cube LR squared. And we are saying that what? At a fixed frequency, omega E will be constant, right? Then if the supply is also fixed, then this will be constant. The resistance is constant. The pole pair is constant. Okay. So then the only thing that may be changing here is what? Maybe the slip. Okay. So if all these are constant, this I can rewrite this as what? Okay, let me write 3v1 squared times RR times P times S, all divided. Let me bring omega E outside. I'm going to get RR squared plus what? S squared omega E squared LR what? Squared, right? Then I can say T is equal to what? 3v1 squared RR times what? P, all divided by what? Omega E times what? S divided by squared plus what? S squared omega E squared LR squared. So everything over here is what? A constant. If everything here is a constant, I can replace this by what? A steady constant K. So I'm going to get Ks divided by what? RR squared plus what? S squared omega E squared LR squared. Okay. So basically it means that even this a constant, this a constant, this a constant. If the supply is constant, this is a constant. So that means any change in T will just be what? At a result of what? The change in what? The slope. Okay. So then that leads us to what? This graph over here. Yeah, so that's what you have here. So then that leads us to this graph over here. So what this graph is saying that, so this is a graph of, this is a torque speed characteristics of what? The induction motor. Okay. So this is speed increasing, the rotor speed increasing from 0 to what? The synchronous speed. And so this is increasing speed. If this increasing speed, this is increasing what? Slip. Is that okay? Because at the point when the rotor speed is equal to the synchronous speed, your slip will be 0. The point where the rotor speed is 0, your slip is what? 1. Is that okay? Then you can see a certain characteristics over here, that when the torque is very low, the slip is very low, at very low slip. Okay. The torque speed characteristics is what? Linear. It's like it's kind of a straight line. Okay, so that's at a very low torque. Okay, so what is that telling us mathematically? You see, in the denominator here, we have the square of what? The slip. And here we just have what? The slip. Is that okay? So at a very low slip, that's as the slip, the closer the slip is to zero, the closer the speed is to zero, the square of the slip is less than what? Just the slip. Okay. So then r squared will be far greater than what? S squared omega e what? LR. Okay. Then we can say that what? Since this is far greater than this, then we can what? Ignore this. Doesn't make sense. Okay, let me go to another. So the torque equation is what? The torque equation is 3v1 squared. Okay, let me just write that out. So we have k s divided by r squared plus what? S squared. Okay, you let me write. So the torque is equal to 3v1 squared r ps all divided by what? Um, omega e, then r squared plus s squared omega what? Omega a cube, then times what? LR squared. So that means at a very low slip, this here becomes what? Very small. Okay, then we can approximate this T to be equal to what? 3v1 RRPS, all divided by what? Omega E RR was squared. Okay, if this happens, we can multiply the denominator by what? Omega E, and then the numerator by omega E. So that's going to give us T equal to 3v1 squared, or sorry, 3v1 squared RR times P times S omega E divided by what? Omega E squared RR what? Squared. Okay. Then what we have here is what? Omega slip. Is that okay? So then this can be written as what? TE equal to 3v1 squared P times R times what? Omega slip divided by what? Omega E squared what? RR. Is that okay? Then if that's the case, then TE, because every other thing here, what? All of this here is what? Is a constant. Right? If the supply is constant. So then TE is proportional to what? Omega or slip. I hope that's okay. Yes. So that's what we are saying over here. Okay. So if the slip is very small, then the torque becomes what? So if the slip is very small, that's here. The torque becomes what? Proportional to what? The slip frequency. Is that okay? Yeah, so that's what you have over here. So we are saying that note that the gradient of this curve can be altered by what? Changing Vs or changing V1. That's the magnitude of the supply using what? A variable or three heuristics. Okay. So yeah. Okay. The rest, I think you understand this. Yep, yep, yep. So these questions I've already solved them in video, uh, the video that was already recorded. Okay. So when you get to this point, you end over here. Like I'm going to end here. Then the continuation is the video two. Okay, where I solve all these questions. Okay. So yeah, we end this one here. I'm going to do another video that solves the second set of questions at this point. Okay, yeah. Yeah, so I'm going to do another video that solves these questions. Okay, that will be the video 3. Okay, so, yep.